it says it will start soon. And we are on. Good. Okay. So I'm going to go back. Whoops. I'm going to go back. So you guys said you had something like this was number 5 from the homework?
Yeah.
Okay. So you guys were talking. So you have a sheet metal fabricator is going to cut identical squares from the corners of a 20 by 8 centimeter piece of sheet metal. It's going to be bent to form an open box top, right? So the first thing is did you guys kind of ask yourself, like, should I just draw the 20 by 8 rectangle and start there?
Yeah.
Okay, so let me just make sure I'm getting, okay, this is working. Okay. So the first thing is you're looking at this 20 by 8. So this is 20 by 8. And then they want to cut off. So if you were to cut squares off, so if you're cutting these little squares off on the end here, it's those squares that you're cutting off right here. Okay. So we're cutting off those squares. And then imagine that once we get rid of those squares, we can fold along these dotted lines. And if you fold up, this up, that, you'll have like an open box. Okay. Do you understand what I'm saying? Like if I cut the squares off, so it's going to look, so, so the net, if you remember from geometry last year, the net should look something like this, right? By cutting those squares off. So if you go ahead and you fold along those dotted lines and you fold up, you'll have this little open box.
Yeah.
Okay. Oh, look, switch a net to describe the situation. There's A, right? So, because that's what they're doing, and that's how they form these boxes. Now, you're trying to write a function for the volume, and if you remember, this is if I draw this, this is actually in the shape of a, what kind of shape is this? Do you guys remember what it is?
Parallelogram.
That's a prism.
It's going to be a rectangular prism. So this is my shoddy looking box, but this is open here, okay? Yeah, I know you guys are like, oops, okay, I said the wrong thing, and that's okay. All right, so now, so your volume, and if you remember, what is the volume of a box? It is length times
width
times height. Now, how many, so that means, and think about this, volume is measured in what units?
Units cubed.
It's in cubic units, exactly. And if you notice, dimension 1, dimension 2, dimension 3. So you're talking about your length, your width, and your height. And when you go up, it's going to be measured in cubic units. That's why it's the way that it is. That's why volume is what it is. So if I want to write the function for the volume, I have length, width, and height. But the problem is that, like, yeah, I can say length, width, and height. But when I'm looking over here, I have to go ahead and figure out how to write the length, the width, and the height in terms of some value we're going to call x. So if I go back over here, I'm going to call these little squares that we're cutting off, those lengths are going to be called x. All right? Are you all following?
Yeah.
Okay. So when I fold this up, so when I fold my box up, this is x here, this is x here. So when I actually physically fold it up, you can actually, you know what? Now watch what I'm going to do. Check it out. Do I have a scissor? I don't have a scissor. I'll be right back, okay? All right. I'm getting a scissor.
I have this part. I still have D. Yeah. Oh, yeah. Oh, wait. I don't think I did. Apparently, the other French class wasn't as bad as ours. I know.
Okay. So here is my piece of paper. Even though I'm writing on it, may as well do that. I'm cutting the corners off of each one. Right? They're not going to be exact because I'm trying to do this fast, but I'm legitimately cutting off the corners here. Okay? As I cut them off, cutting here. We can all see me cutting away. Yay, dishwash. Okay, so this is going to be some makeshift nasty little box. So if you look at it, this is what the net looks like, right? When we cut the squares off. Yeah? So now I'm going to fold them. I'm folding them up. Thank you for yesing me because I do need that kind of response because we are in this together. So I'm folding this. And we have this makeshift box that should look good. If I actually made nice squares, you can actually see I have a box with a top, an open top. Yeah? So what I was trying to point out to you guys before is that when I have this as my net and I fold it up, those squares that I cut off, this length here from here to here is x. And that represents the height of the box. You all ready?
Yeah.
Okay, good. So now I'm going to go back. Did this help? Was it worth it trying to find my scissors? Yeah. Okay, good. Well, Aaron, thank you. See? All right. So now we're back to this. And I don't know where it went. Oh, here it is. Okay. So now when I'm looking at this, this is going to be x. These are all x's all around. So if I asked you guys, I wanted to find out. So I know, let me just go back over here. Don't get all crazy on me here. Okay. So I know that my height is equal to X. So the height of the box is X. I have to figure out what the width is equal to, and I have to figure out what the length is equal to in terms of X. Because when we're doing these problems, the goal is to make sure we're only dealing with one variable, okay? So now I have my height is equal to X. Now my width is going to be, let's say that this is my width. If I wanted to find out what the distance is from here to here, can you guys tell me what that distance is in terms of X from there to there?
20 minus
2x.
20 minus 2x. Look at you little savages. Yes, because you're taking x off here and you're taking x off there. So we know that this is going to be 20 minus 2x. And then let's go with yellow. And then this length right here is going to be
8 minus 2x.
8 minus 2x. That's delicious. So now we know that we have it. So 8 minus 2x. So now my volume function, I can now write as a function of x. It is now going to be x times 20 minus 2x times 8 minus 2x. By the way, what kind of a function is this? It's a polynomial. What degree is it?
Cubic.
It's a cubic function, and it should be because this is volume, right? It's volume. So now what we can do is we're writing a function, and it's asking you what is the domain for the function. So what I want to do is we're going to jump over to Desmos, okay? And if you guys could do me a favor and tell me what the function is, and I can type it right over into Desmos. And f of x is equal to, I know it's x times 20
minus 2x.
2x.
And then 8 minus 2x.
8 minus 2x. Okay, so I have to adjust my window a little bit, as you can see. So I am going to go out. I'll make this 16 because I can't see anything. And then I got to go way, whoops. No, I want to go way higher with that. 76, let's say. Nope, got to go even higher. 176, there we go. And then we'll go 176 here. And then we will change this to, nope, that's fine. We're going to change this to like 20. Nope, that's too big. See how that's too big? So we'll change that. I don't think we need to, hold on. I need to make this a little bit more negative, don't I? Okay, too. All right, so here we go. So this is the cubic function that represents the volume of the box, right? So you can actually see this pretty little cubic function, but I'm going to go bounce back to what we have over here. And we have to think of values for x that are going to make sense, right? Are you all with me?
Yeah.
Okay, so here's my thing. Can the length of, can I have a height of, let's say, 20? Can I have a height of 20 centimeters?
No.
Why?
Because you can't have either side be negative, and if you
Right. So we know it can't be that. Can it be 15?
No.
No. Are you feeling a limitation on it? What are you feeling the limitation as?
4.
4. But what if we did? So what if I did? What if I did 5 here? Is 5 okay?
5's okay with the 20 minus 2x, but not okay with the 8 minus 2x.
So it's not okay then, right? So you said, Aaron, you said 4.
Yeah. Well, I don't think it's 4.
It can't be 4, right? So now let's go take a look over that pretty little graph. What do you know?
Oh.
At 4, it becomes negative.
Yes. So in other words, this is basically saying that if you're looking at this, that anywhere between 0 and 4, my height can be anywhere between 0 and 4, but it can't be anything beyond 4 or it can't even equal 4. So all of these values all along here are the domain with which I can create my box.
Okay.
Okay. So now we're going to jump back over here. And where's my little pen? So now when I look over here, I know that my domain is going to be 0 less than x less than 4. So it's got to be somewhere between 0 and 4, right?
All right.
Yeah.
Okay, that's the best we can do. So now if you want to, it says what is the maximum volume of the box? Going back here, what do you think that corresponds to?
That'll be the maximum.
The maximum, relative maximum at that point. So whatever this point is, and that's where you can take out your calculators. And I believe it might be 1 point. I don't know if it is in fact 1.761 to be exact, but on your calculators, you can put this function into your calculators, and then find out what this maximum value is that will yield the maximum volume that you'll get. So in other words, this is the height, the 1.761. So let's say hypothetically that this actually is the relative maximum point on the interval from 0 to 4. This represents the height of the box. What does the y coordinate represent here?
Volume.
Volume.
Volume, because remember, f of x is x times 20 minus 2x times 8 minus 2x. This is height times length times width. So this actually is your volume, right? That's your volume function. And if you remember, x was our height, so that means this is the height right here, and then this guy here is the volume of it. So when we go back into, where am I here? Right there. So when we go back in here, and if you're like, okay, I'm just going to do a quick raw sketch of my graph, right? It's going to look something like this, where this is 4 and this is 0. Then yeah, this is my volume, and then this is going to be my height, and that's going to be the x. And that's why right up here, whatever that x comma y is going to be the height that you will yield that maximum volume that we're talking about. Okay.
Yeah.
Okay. So we feeling good about that one?
Yeah.
Yes.
Great. Okay. So now, all right. So let's take a look at this one. So this one is even more interesting. Okay. It's a cutie. It's a cutie patootie. And it says that a rectangle has its 2 lower corners on the x-axis and its 2 upper corners on the curve y is equal to 16 minus x to the 4th. Okay. Right. A function a of x that represents the area of a rectangle is a function of x. So the thing is if I were to plot a point here and I were calling it x comma y, what would be the area of this rectangle if I were to call that x comma y?
2x times y.
X
2x times y. Very good, right? Because this right here, because this little piece here is x, and that's another x over there. So therefore, this is going to be 2x, and the height of your rectangle is y. All right, everybody all right with that? But the problem is right now, the area is in terms of both x and y. So I got to figure out how to get y out of there so it's only in terms of x. Does y equal something in terms of x?
If you put the equation in.
Yes, exactly, because it's not just the equation. It's saying that y is being defined as the relationship that it's 16 minus x to the 4th power. That's literally what it's saying. So yeah, this is your relationship. So this right here is going to be your best friend. So now watch what I can do. I am now writing this as a function of x. So I can do 2x times 16 minus x to the 4th. Isn't that nice, right?
Yeah.
So we have a of x is equal to, so it would just be, what is that, 32x minus 2x to the 5th, right? So that's your area function. So that would go in here for a. And then it says find the value of x that maximizes your area, okay? So you're going to find it. Now, what is the degree of this one?
5.
It's a 5. So what we're going to do, again, this is where you get to go onto your calculators, okay? But I'm going to go onto Desmos because we can actually see it. I'm going to turn this off. Can you guys tell me what that function was? Do you remember what it was?
32x
minus 2x to the 5th.
Yeah. So 2x minus, wait a minute.
32x.
Thank you. Minus 2x to the 5th?
Yeah.
Okay. So again, when you look at this, here's what 32x minus 2x to the 5th looks like. What point, so, what point, and by the way, if I asked you for the domain of this function, right, we're talking about the area of the rectangle, what's the domain going to be?
-2 to 2.
Okay, so let's go back, because if I go back and if you say from -2 to 2, in the context of this problem where we're talking about the area.
It's negative x to negative to x.
Say that again?
Is it negative x to x rather than -2 to 2?
Well, no, it's not that. It's just that if I were thinking about the area of a rectangle, yes? Isn't the area always positive?
Yeah.
Yes.
Right? So I just feel like if you put a negative value in here for x, you're going to defeat the purpose of what the area is. Like the dimensions can't be negative. I mean, the coordinates themselves can be negative, but when I talk about the dimension of x, it's not going to work. It has to be positive. So when I look over here, the main thing that I'm looking at is where my x values are going to work, where the area is going to be positive. And that's on the interval from
0 to 2.
0 to 2.
0 to 2. So technically the domain of this function is from 0 to 2. And then when I go back, and then if you want to go ahead and find out where it's saying where you're trying to find the X value that maximizes the area, what point on here am I looking at that's going to help me maximize the area?
The maximum point.
The maximum, yeah, the relative maximum here. So it's going to be this guy right here. So again, in looking at this function over here, this g of x function, this is the function that represents the what?
The area.
The area. So the x coordinate represents the x, the part of the dimension of the rectangle, but the 34.24 actually represents the
Area.
Area.
Very good. So it is this right here. So it is these values that are going to help us determine what's going to actually maximize what we needed to maximize. So I'm going to go back over here. Do you see those numbers?
Mhm.
Yeah, because I'm going back to the other page. So I believe I saw 1 point. Where do I keep doing my pen sheet?
337.
All right, so over here, so it's 1.337, comma, what was it?
34.24.
34.24. Okay. So on that graph, which I'll just do a haphazard picture of, right? And so it was like that, right? So this isn't bad. So this is 2, 0, and that's 0, 0, right? So it says give the full dimension. So now find the value of x that maximizes the area, and we said that x was equal to 1.337. But let's be careful because it says give the full dimensions of the largest rectangle. And if you remember, our rectangle was actually 2x, I'll make it look like an x, by y, right? So that means the dimension of this rectangle is going to be twice of the 1.337, which is how much?
2 point something.
Wait, hold on.
2.674.
2.674 by, and then the y coordinate you'll find by doing this 16 minus that 1.337 to the 4th power. Which is?
That makes sense.
12.8.
Is it 12.8? You guys all agree? I didn't do the math, so I'm just assuming you knuckleheads did it. Is it?
Yep.
Okay, so what was it? 12.88?
12.8.
My pen died, so I'm doing this on my mouse. Okay, with my mouse. So it's 2.674 by 12.88 because it says to give the full dimensions, because if you remember, the area of the rectangle was 2x by y, not just x by y. Okay? And if you do 2.674, remember this is all rounded times 12.88, we should get that 34.24 or whatever. But if we're rounding, it's going to be slightly off. Because remember, this value right here is what's going to yield the maximum area that we can squeeze under this quartic function, okay? Because that's what our goal was. Our goal was to figure out how to squeeze as much area of a rectangle inside of that quartic, okay?
Mm-hmm.
All right. So what other questions do you have? I'm going to go back.
I'm a little confused about the question where how is the let me check it. The
Well, I have it up here so you can tell me what
division the same as direct substitution.
Oh wait, I think I get that.
Oh, then what we're going to do, I'm going to stop presenting, and then you're going to get on, and we're going to see what you have to say. You're going to be a presenter, okay?
Okay.
So let's see what you come. No, I'm just because this is beautiful.
Wait, I have it written down, not on my computer.
That's okay, but can you hold it up and kind of talk to us about it?
I guess. Well, I mean,
instead of doing that, just everybody pin Erin. Don't go on present because it'll go on backwards. So if we all go and go pin on Erin, let's see what you got. And just if you can hold something up and then just
all I did, I was doing it before we got on this. All I did is I did for the first problem in my classwork yesterday. I just did them both out, and I feel like that's just the work of doing them both out. I didn't write down anything or anything like that. But
okay.
But
so
I think
it's doing them side by side. So what does that tell you?
It tells me that since in both ways, the things that aren't changing are the x cubed and the x squared and all of that. So if those aren't changing, they're constants. The only thing you can really compare are the coefficients, and so that's what the the synthetic division. That's what that does. It compares the coefficients, and or just use the coefficients. I mean, this is like plain stuff. Like I didn't really think through it yet really fully, but like all I know is that because the x's are going to be the same, they're constants. So what matters is comparing the coefficients.
Okay.
And so you're taking that that root, which is equal to x, you're doing that times all of the coefficients in the equation in a synthetic division, and that you're also doing that times all the roots in the standard. My God, I can't think of the names of them. Direct substitution as well. It's just the exponents, but it doesn't really matter because they're the same anyway.
So my question to you is do you think that you guys, because there are 3 of you, that you 3 knuckleheads, 2 of you live together, by the way, but they don't communicate with one another, which is actually amusing. Haha. So anyway, is it possible that you guys can somehow formulate, because I think you're onto something, Erin. I think you're starting to see the pattern.
Yeah, but I don't think I've formulated anything.
Right. Now, if you 3 could put your heads together and just start formulating it, that would be kind of cool. So you can create your own Google Hangout, or if you want to stay on the line, but I'm going to stop recording and hang up, and, I'll post what we have here, but we're just going to kind of like, move on from here. Because I feel like we've done a pretty good job.
Okay.
Yeah.
Right. So I'm going to leave it to you guys. So what I'm going to do is I'm going to leave it to you guys to, if you want to stay on the line with one another, or if you want to, go someplace else, I guess, do like a different hangout or whatever.
I'm down for just staying on the line.